So as we begin to formalize the idea of a definite integral, we're going to start off with a definition here that's long, it's a little wordy, so you may want to pause the video and write it down. But I'm going to explain the components of this just a little bit so that we can break it down and it makes a little more sense. So if f is a function that's defined over some interval from a to b, we divide the interval, that interval, into n subintervals, which is what we've been doing. And those subintervals have an equal width that we've been calling delta x. And this is how we've been calculating that delta x. So we let x sub 0 be a, that's the beginning of that interval, and then we have an x1, which is going to be, a plus delta x, and then an x2, which is x1 plus delta x, and so on, all the way until we end up at b, the end of this interval. Then we let x1 star, x2 star be portions of those subintervals, or a sample point in these subintervals, and sometimes that might be the midpoint of that subinterval, or it could just be a point that's in that subinterval that would give us the best representation of a rectangle that would fit under the curve there, such that the ith subinterval is represented like this. So we've got x sub I minus 1 to x sub I, and this is just one of the subintervals for some I value inside this interval. If this is all the case, then the definite integral of f from a to b is defined like this. So this is our definite integral, and this is the Riemann sum notation that we've been using until now. So this new notation means exactly this. So we discussed the idea that if I do take the area of these rectangles that have a height of f of x sub I star, or whatever value within these subintervals we choose to represent the height of each rectangle, times the width of each rectangle, which is all the same, and we add up an infinite number of these rectangles from the first rectangle all the way up to the largest number that we can calculate of these rectangles, and beyond that even theoretically, what we're doing is taking the limit as that number of rectangles approaches infinity. And that's going to get us closer and closer and closer to the actual area under the curve until theoretically we have that exact area. Another way to write this is an integral notation. So from now on, when we write this, we are expressing this just in integral notation, and this is the notation that we're going to be using moving forward, because we have other ways to evaluate these sums other than taking limits of sigma. Provided, so this is all the case, provided that the limit exists. So as long as this limit does exist, and that's not always going to be the case, but provided that it exists and gives the same value for all possible choices of sample points. If it does exist, we say that f, this function, is integrable on that interval. So it's a lot there. Hopefully you wrote it down, but we're going to walk through what this actually means and how we're representing this in integral form and moving away from Riemann sums. So if f is positive, if your function is a positive function, then this behaves pretty similarly to the way that all of our Riemann sums have behaved so far. We can envision having a bunch of rectangles drawn in here, right? Maybe if I'm going to use a left-hand Riemann sum, this would be my first rectangle, and then I'd have another rectangle. And so this is obviously my x sub 0, my initial x value, and this would be x1, and this would be x2, and so on, right? This is what our Riemann sum would look like, and this is so when f of x is greater than 0, this is exactly like what we've been doing. So the Riemann sum would just be the sum of all of our rectangles calculated by f sub, in this case, I minus 1 times delta x, all right? And it's the sum of the areas of the rectangles. But once we take the limit of these rectangles' sums as the number of rectangles approaches infinity, we get a much more clear picture of what's going on under this curve, and it would go up to b. And that space there is what will be covered in the integral when f of x is positive. So if I take the integral from a to b of the function f of x dx, that's the area under the curve from a to b, which would be the same thing as taking the limit of these rectangles as n approaches infinity. And a couple of components of this integral that I want to point out, because there's some vocabulary that I'm probably going to use in the rest of these videos. So this symbol right here, that curve, is called an integral symbol, and it indicates that we are essentially taking the sum of a bunch of rectangles as n approaches infinity. f of x here is representing the integrand, which is the function that we are integrating, or the function that we are calculating the area under the curve of. The a and the b here are representing the limits of integration, so that's telling us where in our domain we are focusing on this function f of x. And then finally that dx, which replaced our delta x, is just stating that the independent variable in this situation is x. Okay, so these are some terms that we're going to be using, and so if f is positive, then we would say here that this integral from a to b of the integrand f of x dx would be a number, and that number would be positive in this case. There's another situation that we could encounter where our function could be sometimes positive and sometimes negative over the interval from a to b. So in this case, we're going to have, and I'll draw in the rectangles, we're going to have some positive areas, right? If I use a left-hand sum, we'll have some positive areas here, but we're also going to have now some that are negative. And that would be these rectangles down here. So you can see a situation now where we're going to have some positive values, so these would all be positive values here, and some negative values. So I'm going to take the sum of the rectangles from A to wherever this point is here, and then I'm going to have the sum of these rectangles from that point on our interval to this point on our interval, and then these rectangles will be positive. So I'll have some positive, and some negative. So how do we handle this? Well, if we're dealing with rectangles, then we've got some positives and some negatives, and we're going to subtract them. But let's discuss this within the context of an integral. So this is going to be the integral from a to b of our function f of x dx, and that's going to be equal to the positive areas minus these negative areas, so we'll say where A1 is the area above the x-axis and A2 would be the area below the x-axis, and we call this the net area. So the idea of net area is taking our positive area and subtracting our negative area to give us the area in the middle there. What do we end up with? Do we have more negative area or more positive area? And that's what we're doing when we calculate that integral over a domain where our function is sometimes positive and sometimes negative. So here's an example of where we might want to convert one form of the integral from the Riemann sum into integral notation. So we're asked to express this limit as an integral on the interval from 0 to pi. And so we're given a Riemann sum here, and it's the limit as, and this should say n approaches infinity, not x. And it looks like it's probably a right-hand Riemann sum because we can see that these are all x sub i's, not I minus 1. But whatever the case may be, if n is approaching infinity, then we are approaching the exact area under the curve. So what's the function we're dealing with? Well, it looks like the function that we're dealing with is this component, right, because our delta x is on the outside. And so that function appears to be, if I call it f of x, x cubed plus x times sine of x, because these are the places where I would be inserting my x values to evaluate this function and to get the heights of those rectangles if I'm thinking of it in the context of a Riemann sum. And it looks like I'm trying to evaluate it over this domain from 0 to pi. So what I'm going to do is I'm going to say that this would be the integral from 0 to pi of x cubed plus x sine of x. And that's a little sloppy. Let me rewrite that. Sine of x. And you'll notice in our integral notation, we don't have delta x. We just identify the independent variable here to be dx rather than delta x. So this component turns into dx. This component is still our function. We need to evaluate that. And then the domain that we've chosen to evaluate the function over becomes the endpoints of our integral to tell us where we are choosing to calculate the area under this curve. So you're going to have some Khan Academy to work on that's going to continue to solidify the information that you were given in today's notes. And then on Monday, we'll start doing some more examples with this kind of stuff.